Hello, this video is about system identification again. Someone sent me some data to optimize, and it's a heater system, and I'm trying to optimize it or identify it as a system, second order plus dead time system. But as you can see, it really could have been identified as a first order plus dead time because one of the time constants is so short relative to the longer one that could have got by with just one time constant. Anyway, this is what the incoming data looked like. And you can see this is the control signal. And this is like 0 to 20% is what it was doing. I don't know why it was making little jumps here, but anyway, 0 to 20%. And then the cyan line, the light blue line, is the process variable or the temperature, and you can see it's quite coarse. It jumps in steps of a quarter of a degree. This is degrees over here. And also it seems to toggle between 2 bits. It's almost like the data was taken with the 8-bit A to D device, and it obviously was kind of noisy because it was jumping up and down like this. At least it wasn't very, the data is not very smooth. And that was actually one of the problems. There were 2 big problems to get started with. The first one is, if you take a look at, this is one of the initial system identifications, and you can see that the estimate goes down and then goes back up, and I wondered why. And after a little bit of tracing through things, what I found out is that the control output is not starting at 0, it's starting at 5%. So I have to extrapolate this in negatively to as far as the dead time. So whenever I'm using a dead time, take a look at this output here, but I have to apply it back here. So what happens is you have a queue, all this data, but I have to index into it back as many time periods as the dead time happens to be. So what happened is I was indexing back beyond 0, and because I assumed it was 0 instead of 5%, I was using a low number, and this was obviously the temperature was decaying towards ambient, which is down here someplace, which has me kind of interested in where it really happened to be. So anyway, you can see that the temperature goes up, and then this is a very sharp turn up here, and this is what makes me believe that the really could have modeled this as a first order plus dead time, because if you see here, this is the results that I got on this system identification. This is not very good, it's not very accurate, but I get 0.72 degrees per percent control output, but the time constant here is what I want to look at. This is only 0.03 minutes, and this is so short compared to this one that honestly this could have been identified as a first order plus dead time, but my code is set up for a second order plus dead time, so that's what I'm using here. For all practical purposes, you could just add these 2 together and call that your integrator time constant, and I think you would be good. Then you could use the gain from up here. Now, what I did to fix this problem is 3 things. One is that the time didn't start at 0. I don't know if that really made a lot of difference, but what I did is I took the first reading and I subtracted that time offset from all the readings, so I shifted everything so the time begins at 0. Another thing I did is I used a Savitsky-Galais filter, and that gives kind of a weighted average, and it smooths the data out. And there's a difference between smoothing and filtering. Smoothing is done after the fact, and also it's symmetrical. So it doesn't effectively change the average values in here, but it does make the data look smoother, and you'll see that in the future. And then also I extended the 5 degrees out so that before, when I at time 0, but I'm indexing back by the dead time instead of getting a 0, I'm getting 5 degrees. So in the future, the temperature does not drop like it does in my estimated value here. So this is one of the early ones, and it is not very good. Let's see if I have any others in here. This is least squares. This is a bad one. Before I had figured out what the initial conditions could be, I found out that there are some local minimums, and you could easily fall into them. In this case, what happened is I had a guess that was bad, and what would happen is it would terminate early, and or get stuck, and so I'd end up with something like this, and this definitely is not right. You can see that the temperature drops again, but what you should notice is by this time I had already figured out that I should use the Savitzky-Gallet filter, and I've smoothed out the data by quite a bit. And this is important, and because the person I was doing this for, if they're using a PID, they really shouldn't use the derivative term with the amount of quantizing error that this one happens to have, because taking the derivative of these values is not going to give you decent results unless you apply an awful lot of filtering. So I would just use the PI on this data, or better yet would be to get a higher resolution A to D device to measure the temperature. So given that, you can see that my best solution, let's see if I can figure out my best solution. My best solution is here, and you can see that the temperature gain is 9 degrees per percent output, and the time constant is still short. The first one is short, but the second one is long, and this makes sense given the data, because take a look at how the temperature, the actual temperature is declining here. It's almost in a straight line, and so basically what that's telling me is the time constant is very, very long, and so a long time constant like this makes sense. And you can see the dead time is a little bit about 2¼ minutes, so it's not real short, but it's very short compared to the first time constant. So what that means is that I really should have used a first order plus dead time model. So let's take a look at some of these others. Okay, this is the Levenberg-Marquardt, and this is a line search, and I'll explain these later. And you can see they all get different answers, and part of it's because they would hit the local minimum, and this is one of the initial ones, and you can see that the initial guess I had made for the time constant was too short, and you can see this looks like it's decaying, but again the data shows that it's if it is decaying, it's doing it at a very, very slow rate, so it looks like it's almost linear. So let's take a look at the programs that I used, and we'll start out with the one that worked the best, and that happens to be the minimize program in SciPy, and I use the Levenberg-Marquardt algorithm. No, this one's the Nelder-Mead, and basically the Nelder-Mead is a very simple system. It does not use derivatives because I've got 5 parameters to optimize. I got the gain, the 2 time constants, a ambient temperature, and a dead time. So that's 5 things. It would start out with 6 points. And what happens is that it starts out with 6 points around your initial guess, and then it takes a look at the mean squared error of the worst one, and it moves it halfway towards the center of the other 5. And then it takes a look at that, sees if it's better, and if it's better, then it might extend beyond the average, so that way the minimum can move. And eventually this will get to this gets the best solution. You can see that the mean squared error started out with 0.04 and ends up at 0.162, which is the lowest mean squared error I could find. All the other mean squared errors that were terminated have to be local minimums, or if they weren't local minimums, they were places where I had the learning rate for the gradient's descent so big that it couldn't either negotiate the turns around the that it had to make. It was just too big, so it always gets stuck, or the steps were so small that it couldn't get out of the local little pit it happened to be in. So again, there were a lot of local minimums, and what I like about the Nelder-Mead is that I can start it out at any one of these solutions here, and it will get to the final solution. And let me just show you that. I'm going to, okay, this happens to be initial conditions that will get me towards the, it normally gets me to a local minimum and not the global minimum like these parameters. So if I run this right now, and it will take about 20 seconds, and you can see this gets the same initial conditions. And let's just, you have to wait for a second. What I should have done is displayed the parameters. Okay, this is, okay, got the same answer. The Nelder-Mead would always get to the global minimum, and no matter where I started it. And whereas all the other ones, they would either get stuck, or sometimes they would blow up. Now, let me explain my concept of terrain. Now, this is 5 dimensions, so it's kind of hard for people to think about things in 5 dimensions. So I'll just boil it down to a simple 2-dimensional example. Excuse me. Think of this as trying to follow a stream down to the sea, where the sea is the global minimum. And what you're doing is you're following the stream, and in this case, the stream has a small shore and banks, and then there's a plateau on either side where it's rather flat, or maybe not, but we don't know what it's going to be like. So what happens is that the solutions are best if I can find an initial condition that gets me within the banks of the stream. If I get take an initial solution that is outside the banks, I'm just at the whim of whatever the terrain happens to be like outside the banks, and it could go off in any direction, and sometimes it gets lost. And that's the problem that I ran into many, many, many times until I managed to find a solution that would get me into the between the banks. And then what happens is then you have to be able to follow the stream down to the sea. Now, this stream does not go in a linear fashion. It has lots of meandering turns, kind of like, well, it's a meandering river or a meandering creek or whatever you want to call it. So if you go in any direction too far, it's going to get stuck. It just won't go. In other words, the mean squared error will increase because the elevation is going up. And what will happen is if you take a step too big, you get outside the banks, and then you get lost. It could go anywhere, and the system blows up. So the whole idea is to have the steps small enough so they stay within the stream banks. And you have to have it large enough so that you eventually get a solution. So one of the things I started out with is, just to find out what works, is a gradient descent. And the gradient descent, I'm not going to bother to show it here, but it would basically take hours. And the reason why is because the step size is fixed. It's just one learning rate, and it would sometimes get stuck and in an area, and then what would happen is it would go up against the bank, and then it would get another slope there, and it'd go back and forth in the between the two banks, just bouncing off the banks until it eventually might find a direction that goes downstream. So, for instance, maybe only 1 out of 10 tries would actually make the mean squared error drop down. And that's why it was so slow. Also, if I made the steps smaller, then again, the steps were just too small. So one of the things that I did is I used an improvement on it. And believe me, I tried many of the other gradient descents that you see on the internet, and they don't work for the same reason. They don't adapt the learning rate. So that was one of the things I had to try very quickly. And let's see if I can find the learning. I'm looking at my screen over here. Let's see, go here. Okay, now the learning rate I chose to be very big. And you would think, well, that's bad because I'm going to get stuck. I'm always going to be going outside the banks. Well, what I did is I added a check, and this is my routine here. I added a check to see if the mean squared error dropped down. And if it wasn't better, then what I would do is I divide the step in half. And I would keep on dividing it in half until it would eventually move and get a better solution. So this solution worked much better. And if I run this for a second, you can see what I was doing. Okay, now you can see this is this is one of the ones with a bad guess, and but you can see that it's going down. The mean squared error is dropping down fairly quickly, but the alpha with the learning rate, it's what I call the learning rate, is changing, and it goes down and up. It gets as small as it can, and if it gets down to 10 to the minus ninth, in other words, anything less than 10 to the minus eighth, is going to, I'm going to take that step anyway, but hopefully it's so small that I stay within the banks and I don't get lost for being out on the plateau or outside the banks. And this method worked fairly well, but it would still take a long time. You can see that this has dropped down and made some pretty big improvements, and but this would not find the global minimum if I started in the wrong spot. If I start in the right spot, then it would. So another method that I used is a line search, and let's see if I can find my line search. Okay, I'm looking at, well, I'll just explain it. The line search basically would take a step in one direction, and I made the step small. And the reason why I made it small is so that it could maneuver around all the twists and turns. But if the mean squared error went down, then I would keep on stepping until the mean squared error was no longer dropping. And that way, what I did is I was making it so that it could do the equivalent of a bigger step, but it would just take more smaller steps. And the reason why this worked is because I could find the derivative once, or the gradient once, and then I could just keep on using that same gradient over and over and over again. So it was relatively fast as far as how it got down to the minimum. And then another method I used, which I didn't think was going to work, and I saw this on the internet, and I go, geez, it won't work, but I gave it a shot, and it turned out to work out pretty well. And it is a coordinate search. See, all these routines are the same until we get down to the this gradient descent part. On this gradient coordinate search, instead of finding the gradient and going in a combination of 5 different directions in 5 dimensions, and I was thinking, well, what do you do in an artificial intelligence type application where you happen to have, well, thousands of points that you got to take a look at, and taking the derivative of finding the gradient for 1,000 points is not practical. So, they talk about doing it in batches. But one person said, well, why not just do one item at a time? Because it's real easy to just define the derivative of each one in turn and then have it do a search until it gets to a minimum and then do the next one. And you see that's relatively efficient because you're not going to have to manage to move with all the constraints of, well, in my case, 5 different parameters, because I have to have 5 different, has to satisfy 5 different parameters to keep the minimum squared error at a minimum or to reduce it. So what I'm going to do is I'm going to just show you how this works. And you can see this is going down fairly quickly, and I'm just going to stop it right here because it'll just take up time. And here I'm starting at the wrong position. Again, this is not going to get me to the global minimum. It'll get me to a local minimum. But you see it's using the third item. You see I've got the alpha. That's my learning rate, and that changes depending upon whether or not I get stuck. This is my gain. This is the first time constant, the second time constant, the ambient temperature, and the dead time. And you can see that it just kind of alternates between all these different ones, just moving one at a time. And it gets down to a minimum, although not global, pretty quickly. And the thing is that I would take a look at these and I would be able, I spent a lot of time just looking at these. Now I would just stare at it, but I'd do something else and just monitor the output. And I can get an idea of whether or not it was getting stuck by whether or not these numbers, these mean squared error numbers were changing. So the point is that sometimes the data that you're working with is not a nice bowl or concave type of terrain like what you see on the internet where the instructors have something with x squared plus y squared. On that system, anything will work. I found that all these other systems like Adagrad, Nestor's accelerated system, RMS Prof, and others, they did not work because they didn't change the step rate, the effective step rate fast enough. Whereas in what I'm doing, I would get stuck and then I would start changing the gains, the alpha, the step rates right there until I got something that worked. And that's why my line search and my gradient descent with the dividing by 2 worked so well. Another method that I'm really a fan of is my least squares, and I can find that over here. And I'm a real fan of the Levenberg-Marquardt. Okay, this is using the SciPy least squares, optimized least squares. And let's see, down here you can see, here I am. Oh, this is using, this would be, Levenberg-Marquardt would be this one. There's 3 different options for the least squares. And if I run this, oops, can't have bounds. Oh, that's a problem with the Levenberg-Marquardt, is you can't have bounds. And that's what I like about my gradient descents, is I can do whatever I want. You can see that this is relatively fast, but I started it out close to the local minimum, and it doesn't move outside the local minimum. And you can see the mean squared error is pretty short, pretty small, but I know that it is not the global minimum. It's not the same one that the Nelder-Mead got. The Nelder-Mead is definitely the best because it would always get to position. It's also very efficient, doesn't require derivatives. So basically, I had to try many of these different systems and see which one would work. Finding initial conditions where I was within the banks of the river or the stream was kind of a trial and error type of system, and to give you an idea of how I did it initially, I would, after each iteration, I would make it so that it would plot the estimated value, which is this red line here, and what I would do is then I would manually adjust the parameters until I got this to get close. So it's basically a step-by-step process, because initially when I would try the initial values, the estimated value would go all over the place. So I kind of had to do some manual steering just to get in the ballpark. And then finally I was able to use these other algorithms and do a search. So another item that I want to point out is that how do I know that this stream is meandering? Well, one of the things that I did in the gradient descent is I make it so that instead of plotting out the parameter, I would plot out the change in the parameter each iteration, and I could see it go positive, minus, positive, minus, positive, minus, positive, minus. And what that was telling me is that it was basically bouncing off the banks of the stream. And then another thing I would notice sometimes is that the dead time or a gain would change by quite a bit, and it would go down and then go back up. Let's see if I can find that again. Let's see, heater, coordinate search, minimize. Okay. What I'm going to do this time with the minimize is I'm going to plot the iterations. And you can see that I started out with a very low, this is at the local minimum, and you can see that the gain is increasing. Now it finally got up there. Let's just stop it. Whoops, shouldn't have done that. Okay. You can see that it changes. All of a sudden it's at 1, then it just makes a radical change going up. And then you can see the time constant makes a big change. And you can see that the temperature makes a big change. So what I would notice is that sometimes the values would go up and down in search of, trying to follow the meandering river. But basically, Levenberg-Marquardt rules, and if you were trying to do this with I don't know why they don't use this for instead of gradient descent when they're trying to train neural nets. I saw an example on the internet where a person was trying to identify numbers 0 through 9, and he had lots of training data in a 28 by 28 pixel format, which meant that you'd have 784 pixels. And if you wanted to do a gradient descent on all of that, it would be kind of tough because trying to find derivatives is difficult, especially that many layers back. Whereas with the Levenberg-Marquardt, you would have to have 785, one extra parameter, but you'd only be taking a look at the worst element and then updating that and then getting the next worst element and finding that. So the time wasted would be finding the whatever element happened to be the worst, but it still would be much faster than trying to calculate the gradients for like 728 different items. So anyway, that concludes my video. Hopefully you learn about the pitfalls and some of the effort that it takes to do a system identification. They're not all as easy as you think. In my case, I learned about the extrapolating beyond 0. I added the Savitsky-Gallais and I offset the time, and then I had to again, I would plot the data. I would make a guess manually, and then I would plot the data, and then I'd do another guess, and I would get this close, and then finally then I would let the computer have it, because then I knew the computer wouldn't go outside the banks of the meandering river and get lost. Okay, that concludes the video. Give me a thumbs up if you like it. Bye.